Okay, today we're going to be talking about something called linearization. And essentially, we have come to the end of our learning about derivatives. And one of the major uses of derivatives is to make approximations. And so, if you can kind of visualize here, let's say we have the function 1 plus sine of x. And let's say we wanted to figure out what f of 0.3 is. But we wanted to use, we wanted to get this value without using a calculator. Well, clearly, we don't know what the sine of 0.3 is, so we would be pretty much at a loss for getting a approximate value. However, if we could draw a tangent line to the curve 1 plus sine of x at the point 0, 1, then what we can assume is that for x values close to 0, the value on the tangent line, the y value on the tangent line, should be very, very close to the y value of the function. So then by plugging in numbers close to 0 into the tangent line equation, we can get a very, very accurate approximation of what the value of f of x is at that point. So let's see if we can write the equation of this tangent line. Well, we know that we can use the point slope formula, so y minus y1 is equal to m times x minus x1. Well, we know that the point is 0, 1, but we don't know the slope. So we can find the slope of the sine curve by taking f prime of x. And that's going to be, well, the derivative of 1 is just 0. The derivative of sine is cosine of x. And we're going to plug in 0. And we get cosine of 0, which we know is 1. So our m is 1. So our y value is also 1. So y minus 1 is equal to our slope m, 1, times x minus 0. So essentially we end up getting y is equal to x plus 1. So if we wanted to now find f of 0.3, then all we'd have to do is plug in 0.3 into our tangent line, and we could say that f of 0.3 is approximately, so don't use the equal sign, is approximately 1.3. Now obviously what you can see here is that this approximation is only valid for values very close to where you are writing the tangent line for. So let's say we wanted to find f of 3. Well, we wouldn't draw a tangent line at 0. We would try to pick a point as close to 3 as possible so that that tangent line would closely follow the curve 1 plus sine of x. You can see that the further away we get from 0, the worse our approximation gets. Here's a y value on the line. Here's a y value on the curve. The difference is still not too bad, but it's not very accurate. Okay, I encourage you to do this little exercise here where you're filling out the table of values. And if you use a calculator and get the actual value of f of negative 0.5, the calculator will give you 0.5206. But if you plug in negative 0.05 into the approximation, the tangent line approximation, you will get 0.5. And so you can see that it's still very, very good, even though 0.5 is not extremely close to 0. Now, the closer you get to 0, we see that the actual value and the approximated value are almost identical. So that basically shows you the accuracy of your tangent line approximation. All right, let's say we have the function f of x is equal to the square root of x, and we all know that the square root of 4 is simply 2. But let's say we wanted to find the square root of 4.1 without a calculator. And that's where the idea of a derivative would come in handy. So let me just kind of illustrate for you basically kind of what we're doing here. Let's say we have the graph here. And let's say we have the square root function, so it looks like this. And let's say we have the point 4, 2. So that would be, let's say, right there. And let's say that we can draw a tangent line to this curve. There we go. Well, if we wanted to know, let's say that's 4 right there. If we wanted to know 4.1, then all we would need to do would be to plug 4.1 into our tangent line, and you can see that the y value on that tangent line is going to be very close to the y value of the square root function. So the key here is, if, let's say we didn't give you f of 4 equals 2, if you're looking for 4.1, what you'd want to do is you'd want to draw the tangent line to a point on this curve that is as close to the point that you are trying to approximate, 4.1. So we would pick 4. All right, so let's see if we can do this. So y minus, well, let's just say the point that we're going to write our tangent line is 4, 2. So y minus 2 is equal to the slope m times x minus 4. Now we need to find the slope m, and of course that is the derivative of the square root of x. That's going to be the slope of our tangent line. We've done that before, so f prime of x is equal to 1 over 2 root x. You can work that out later. And if we plug in 4, we will get 1 over the square root of 4, which is 2 times 2 is 4, so 1/4. So we have y minus 2 is equal to 1/4 times x minus 4. And let's go ahead and distribute this and put it in slope-intercept form. So y minus 2 is equal to 1/4 x minus 1. And then we're going to add 2 to both sides. And we get a tangent line of y is equal to 1/4 x plus 1. And maybe we'll write this as 0.25 x plus 1. Now what we can do is we can plug in our desired point of 4.1 into our tangent line, and we get y of 4.1 is going to be equal to 0.25 times 4.1 plus 1, and 1/4 of 4.1 is going to simply be 1.025, once again without a calculator, plus 1, so you need to do a little mental math. So this is going to be 2.025. So basically what we can say is that f of 4.1 is approximately 2.025. But if we use a calculator and we get the real value by plugging in the square root of 4.1, we will find that that value is 2.0249. Hey, look how close our approximation was, 2.025 and 2.0249. Okay, example 3. Find the linearization of f of x equal to cosine of x at x equals pi over 2. So this is just a fancy way of saying write the tangent line of cosine of x at x equals pi over 2 and use it to approximate cosine of 1.75 without a calculator. Then use a calculator to determine the accuracy of the approximation. All right, so pi over 2 we can say is 3.14 over 2, which is approximately 1.57. So it would make sense to use pi over 2 as the closest known point on the cosine of x to approximate 1.75, cosine of 1.75. So let's go ahead and do that. If we take pi over 2 and plug it into our cosine of x function, we will get 0. So the point that we're going to draw the tangent line at is pi over 2 comma 0. But we need the slope. So f prime of x is going to equal negative sine of x. And then we plug in pi over 2 into our derivative. We will get, well, let's just write it here. F prime of pi over 2 is going to be negative 1. So our slope is negative 1. So we can do y minus 0 is equal to negative 1 times x minus pi over 2. So basically we end up getting y is equal to negative x plus pi over 2. And maybe we'll write it again as negative x plus 1.57. And that way, whenever we plug in our 1.75 into here, we will get negative 1.75 plus 1.57, which is going to be negative 0.18. And that is, so what we'll say is that f of 1.75, or maybe we'll write it this way, cosine of 1.75 is approximately negative, this should be negative 0.18. But if I plug in cosine of 1.75 in an actual calculator and get the real value, it'll be negative 0.1782. And you can see very closely, here is our approximate, and here is our actual value. And if you wanted to get the accuracy, you would subtract the actual from the approximation to get the error. Okay, next we're going to talk about a little bit about something called a differential. All right, a differential. Let's talk about it. We know that approximations are not exact. Duh, that's the idea of an approximation. All right, so the idea behind a differential is this. Let's say we call dy dx f prime of x, which is basically dy dx, another way of writing f prime. So if we multiply both sides by dx, we get something called dy, which is a differential. dy is equal to f prime of x times dx. And the values of dx and dy are called differentials. These are very, very small changes in x and y respectively. So basically the idea is this. dy is basically an approximation for the change in y if x is changed by a very, very small value. So if I change x ever so slightly, how will that affect the y change? So a good example of this would be, let's say I measure a radius to be 5, but I could be off by plus or minus, let me write that a little nicer. I could be off by plus or minus 0.02. The question that we would want to know is, how much is my error in measuring the radius going to affect the area of the circle? And so that would be an example of a differential. So let's see how this works on a few problems. Okay, example 4, let's see how these differentials work out in some problems here. We have the function x squared, and we have the point x equals 1, and we are going to say delta x is 0.01, which basically means that we are moving from the point x equals 1 to the point x equals 1.01. So we're moving slightly to the right, just ever so slightly, and we want to first start by writing the equation of the tangent line of f at x equals 1. So let's go ahead and do that. So y prime is equal to 2x. And if we plug in 1, our slope is going to be 2. And we plug in 1 into our function, we get the point 1, 1. So y minus 1 is equal to the slope of 2 times x minus 1. Let's go ahead and clean that up a little bit. So that's going to be y minus 1 is equal to 2x minus 2. Add 1 to both sides. So y is going to be 2x minus 1. So that's pretty simple. There's our tangent line. Now we want to use our tangent line to find an approximation for f of 1.01. In other words, what is 1.01 squared? Without actually plugging in 1.01 squared into the calculator, we can plug 1.01 into our tangent line, and we will get, well, 2.02 minus 1, because 2 times 1.01, so that's going to be 1.02. All right, now if we actually plug in 1.01 into our calculator and square it, then we will get 1.0201. This is the actual value. Now, the values delta y and dy, and find those and compare the difference. Well, delta y is the actual change in y. It's the real change in y. So basically this is f of 1.01 minus f of 1. So let's just see what that would be. Well, the real value of f of 1.01 is what we just found, 1.0201. And the real value of f of 1 is just 1. So the real change in y on that graph as you move from x equals 1 slightly to the right at x equals 1.01, the change in y is going to be 0.0201. Now, the question is, how could we get an approximation of this change in this y value? That's where differential comes in. So dy dx is equal to y prime, so that's 2x. And we multiply both sides by dx, so dy is going to be 2x dx. All right, so x in this problem, it says, is 1. dx is 0.01, so 2 times 1 times 0.01 is going to end up being 0.02. So you can see that our dy, which is, let's just say, our approximation of the change in y, as I'm writing it all out, as x moves from 1 to 1.01. This is our approximation of how it will affect the y value. But this is the real change in y. Okay, let's finish this lesson off with an actual problem. You have the radius of a ball bearing is found to be 0.7 inches with a possible error of 0.01 inch either way. So in other words, they're measuring this radius and they're saying, to our best of our ability, we think it's 0.7, but we know that we could be off by at most 0.01 inches in one direction or the other. So the idea is, what does that slight change in radius measurement do to affect the volume? All right, so we know that the volume of a sphere is, and it's a ball bearing, so it's a sphere, okay, is going to be 4/3 pi r cubed. So let's go ahead and find dv. dv, and maybe we'll put dv dr if that helps you. Bring the 3 in front, so it's going to be 4 pi r squared. We're taking the derivative with respect to r, so no implicit differentiation or anything. So then multiply by dr, so dv is going to be 4 pi r squared dr. dv represents the change in volume, the approximate change in volume, if the radius is possibly off by 0.01. So we can go ahead and plug all this in. So 4 pi, our radius is 0.7. Our dr is the difference that the radius could be measured, so 0.01. So we end up getting plus or minus 0.0616. And we'll say inches. Inches cubed, actually. So the volume could be off by this much if the radius is off by that much. Now the relative error is basically when you take dv, which is 0.0616, and you divide it by the actual volume that you would get if you plugged in 0.7 directly into this volume, and that number is going to be 1.43676. And when we get that on a calculator, that's going to give us 0.0429. And if you multiply that times 100, which is what you want to do in these situations, you'll get 4.29%. So that gives you the error when calculating the volume.